Hello everybody, my name is Sergey Lishkevich. I will represent you the paper Modeling the Evolution of Student Academic Group for Educational Process Management by me, Ksenia Yuditskaya, Vladimir Saishnikov from Belarusian State University. The paper presents the results of fieldwork study conducted with a group of students of Belarusian State University in spring 2025 during telecontrol and navigation course. The aim of the work was to improve educational efficiency. It is based on a few assumptions. First, learning is improved if it use intrinsic motivation of students and collaboration. Second, the academic group of students perform as a nonlinear dynamic system and can be assimilated with the help of Lotka-Volterra equations. And the last, statistically estimated interaction matrix analysis allow to improve group relations. It should be noted that teachers' influence on group development is limited. Also, we should assume that there is no external influence which can produce unpredictable results. Matrix form of Lotka-Volterra equations perfectly match the large-scale problem and was used for the simulations. Four-dimensional equations have been used to explain the process of simulation and is presented at the slide. Full-scale 21-dimensional equations have been used when processing experimental data. Here U sub 1 is state of item 1. Usually it is the population density of the first species. If we simulate wild nature, we have assumed that it should be the size of skills of first student if we simulate educational processes. The same is for other sub-indexes. A diagonal matrix contain the state of items at the diagonal 2. V sub 1 is the intrinsic productivity of the first item, first species, and the same for other sub-indexes. And the most interesting is interaction matrix. W sub 4 and Y, for example, reflects the influence of pair 1 on the species 4. It is 0 if there is no direct interaction. It is positive if the pair improve the health of the species, and negative otherwise. A diagonal contains some negative value which make the system stable. The simulated collaborative activities such as presentation of course materials in class have been used to calculate a full-scale interaction matrix for the academic group of 21 students experimentally. The matrix was built using a series of polls concerning the other students' activity in class and bets on results of their work. Also, this opinion of other group members have been used to calculate the final grade of each student. Hence, the matrix was built using the usual social psychology rules anonymously, indirectly, assuming the real costs and risks of students' decision. The experimentally estimated interaction matrix in the colors of gray is presented at the figure 1. It is 21 times 21 matrix. Matrix analysis is frequently used for solving large-scale physical problems. It can also be applied for simulation of educational process. According to the theory, interaction matrix presented at the previous slide has a set of 21 eigenvalues and eigenvectors. The complex component of eigenvalue spectrum contains the most important information and is presented at the second picture. Here we can see 13 real eigenvalues and 4 pairs of complex. Eigenvalue-eigenvector pairs number 16, 6 and 11 will be further used for illustration purposes. Next picture presents the eigenvector from the pair number 6. The index of participant in the group list is plotted horizontally. The size of its skills is represented vertically. Note that both complex and real values are allowed here. It is reasonable to suppose that each eigenvalue-eigenvector pairs represents some stable interaction pattern. Hence, one can conclude that participants number 11, 21 and likely 9 mostly benefit from presented interaction pattern, and that this pattern should be excluded from the relations somehow in order to improve productivity. This is because of complex eigenvalue. Here we have assumed that the presence of imaginary component of eigenvalue indicates predator-prey relationships in simulations of wild nature. In the same time, in the study of human relations, the complex eigenvalue confirm that one party benefits from other work, signifies inequality and injustice. Let us illustrate with a simple example. A simple predator-prey system, described by the first equation at the slide, have been simulated in order to understand the influence of interaction matrix. Note that second species is not a perfect predator. It has a little intrinsic productivity. One should admit that such situation is more probable in human relations. The interaction patterns is presented below. Both of them has complex eigenvalues. The dynamics of predator-prey system is presented in the picture number 4. Blue line reflects the population of prey. Green line is the population of predator. The important detail of predator-prey system is damped oscillations that can be noticed here. The dynamics of isolated prey first line and isolated predator second line is provided here for as a reference. After such simulation, we can conclude that only predator-prey system has a complex eigenvalue. All other combinations of predator and prey has real eigenvalues. The system of two preys in the state of collaboration have been simulated too. The results is presented at the picture number 5. The first and second line is also provided as a reference. It is separated prey and predator. Blue line reflects the dynamics of two collaborative preys. It is interesting due to higher productivity. And now it can be confirmed that interaction pattern number 6 presented earlier at the picture number 3 is unfair due to actions of persons number 9, 11 and 21, and it should be excluded from relations somehow if a higher productivity is required. Analysis of interaction pattern number 11 presented at the picture number 6 is more difficult, but it is clear that at least student number 8 should be separated from persons number 3 and 14 in order to improve group relations. The axis is the same as at the picture number 3 here. Also, it can be noted here that the presented model is based at the set of assumptions, require careful interpretation, and should be additionally tested. And the conclusions. The educational process was simulated with the help of Lotka-Volterra equations. The academic group was formally presented as nonlinear dynamic system. The efficiency of project-based learning can be improved if each student participation is determined at the base of evolutionary model and statistically estimated relation matrix. Educational process became more effective when it is based on intrinsic motivation of students and collaboration. The opinion of the teacher is correlated with results of simulations. That's all. Thank you for your attention.